initial plus acceleration times time. We can also find acceleration or time from this equation depending on the information we have.
Sometimes you'll see v initial written as v naught with that little zero. Naught just means the starting point. If you use v naught, v final will be just v, with the f left out. It's best, though, to learn them with the finals and initials in place, so you won't get them confused later on.
Here's a crazy mnemonic to help you remember this first equation. Think of a stuttering vat. You know, vivat. V-V-A-T. Or maybe this'll help you remember. V-V-A-T!
Now let's look at this equation in action. Say Not Quite Bright swims with an initial velocity of 1 meter per second, has an acceleration of 0.2 of a meter per second squared, and does all of this for 12 seconds. What is his final velocity?
Well, let's see what we've got here. We have v initial, acceleration, and the time. Just plug those numbers into the equation and crank out an answer.
Plugging in and cranking out, we get that Not Quite Bright's final velocity at exactly 12 seconds after he began is 3.4 meters per second. Go, one-dimensional wonder boy!
Just a reminder, be careful with your units. Remember, instantaneous velocity is measured in meters per second. If you find that your units don't work out, that may be a sign that you didn't set up the equation correctly.
Now, let's use our VVAT equation another way. 100 seconds into a swim race, Not Quite Bright is swimming at 3 meters per second. If Not Quite Bright starts the race by standing in the pool as opposed to diving, what is his acceleration?
Well, we said that Not Quite Bright was in a swim race. When he started the race standing in the pool, his initial velocity was 0.
So we've got t equals 100 seconds, v final equals 3 meters per second, and v initial equals 0.
Now plug and chug. V final 3 meters per second equals V initial 0 plus A times 100 seconds. Use algebra to isolate A, and you get that Not Quite Bright's acceleration is 0.03 meters per second squared.
Suppose you'd ended up with an acceleration of negative 0.03 meters per second squared. That would mean that Not Quite Bright was decelerating. Now, let's move on to the second kinematic equation.
We can use the second kinematic equation to find the displacement, x, of an object. The equation looks like this. X equals v initial times time, plus 1/2 acceleration times time squared. We can also use this equation to find the initial velocity, acceleration, or time, depending upon which information we've been given, and as long as only one of the quantities is unknown.
X v
T
half at squared!
Now let's try this sucker out. If Not Quite Bright is in a speed walking race, and from the start his acceleration is 0.5 meters per second squared, then how far into the race is he after 40 seconds?
Now pay close attention here. The question, how far into the race, is asking about Not Quite Bright's position. So, we know that we'll have to solve for x, which represents position.
Plugging, chugging, and cranking, we get x equals v initial, which is 0 at the start of the race, times 40 seconds plus 1/2 times 0.5 meters per second squared times 40 seconds squared. Working out the math, we get that x, or Not Quite Bright's position, equals 400 meters.
Hey, Not Quite Bright, we'll see you in the next Summer Olympics. But of course, a speed walker would never beat an Olympic sprinter, so get real.
To find the final velocity, we use the third kinematic equation. Velocity final squared equals velocity initial squared plus 2 times acceleration times position. We can also use this equation to find the initial velocity, acceleration, or position, depending on what information we have.
V squared! V squared!
2ax! For example, after a long, hard day of conquering the slopes, let's just say that Not Quite Bright has regressed back to his genital stage of development and is now crawling in a straight line back to the lodge.
Not Quite Bright crawls 2 meters, and his velocity goes from 0.2 meters per second to 0.3 meters per second. What's his acceleration?
So the problem has given us a v final of 0.3 meters per second, v initial is 0.2 meters per second, and x is 2 meters. All that's left is to find acceleration. Now plug, chug, and crank into our equation of v sub f squared equals v sub I squared plus 2 times a times x. So that's 0.3 meters per second squared equals 0.2 meters per second squared plus 2 times a times 2 meters. 0.09 meters squared per second squared equals 0.04 meters squared per second squared plus 4 meters times a.
That's 4 meters times a equals 0.05 meters squared per second squared. Solve for a, and we get that not quite bright's acceleration is 0.013 meters per second squared.
Okay, so we found that not quite bright's acceleration is 0.013 meters per second squared. Just to see if we can, let's see if we can find the time he took to crawl the 2 meters.
We want to figure out how long it takes Not Quite Bright to crawl 2 meters. We've got 3 kinematic equations to choose from. The easiest equation we have to solve for time is the first one, VThat.
V final equals V initial plus AT. For our problem here, V final is 0.3 meters per second, V initial is 0.2 meters per second, and we just found A to be 0.013 meters per second squared. So, 0.013 meters per second squared times time equals 0.1 meters per second. Solve for t, and t equals 7.7 seconds. So, it took Not Quite Bright 7.7 seconds to crawl 2 meters.
Now let's review. The 3 basic quantities in one-dimensional kinematics are displacement, measured in meters, velocity, measured in meters per second, and acceleration, measured in meters per second squared. To find the change in position or displacement, subtract x initial from x final. Velocity is displacement over time, and average velocity is the displacement over the change in time. Acceleration is velocity over time, and average acceleration is the change in velocity over the change in time. The instantaneous velocity or acceleration of an object is that object's velocity or acceleration at a given instant in time.
There are 3 one-dimensional kinematic equations we should know. These equations can only be used when we have an object traveling in a straight line at a constant acceleration. With these equations, we can find instantaneous velocity, instantaneous acceleration, time, and displacement. We use the first equation to find instantaneous velocity. The final velocity equals the initial velocity plus acceleration multiplied by time, or v sub f equals v sub I plus at. Remember that a negative velocity means that the object is going in the negative x direction, and a negative acceleration means that the object is decelerating.
We use the second equation to find the displacement of an object. X equals the initial velocity multiplied by time plus 1/2 of the acceleration multiplied by time squared. Or x equals v sub I times t plus 1/2 at squared. We use the third equation to find final velocity. The final velocity squared of an object equals the initial velocity squared plus twice the product of acceleration and displacement. Or v sub f squared equals v sub I squared plus 2ax.
Well, we've been learning those kinematic equations in 1 dimension, my people of force. Now we'll move to 2-dimensional kinematics. 2 dimensions.
Part 4, 2-dimensional kinematics.
2-dimensional kinematics is motion in a plane, as opposed to motion along a straight line like 1-dimensional kinematics. So, for 2-dimensional kinematics, we'll be talking about motion in the xy plane.
There are lots of different types of motion we can have in a plane, as opposed to motion along a straight line. We're going to discuss projectile motion, uniform circular motion, accelerated circular motion, and then rotational motion. First, let's turn to projectile motion.
Section A, projectile motion.
Projectile motion is when an object is tossed into the air. Its flight follows a curved path. Like if you push someone who's on skis and he goes over a huge jump. You can diagram his flight path like this.
The first kinematic equation we learned in 1-dimensional kinematics is the same one we're going to start off with in 2-dimensional kinematics. Remember the stuttering vat? We use that equation to find out an object's final velocity. We're still in the ideal world here, so we won't take into account things like air resistance.
However, since we're in a plane, we do have to worry about the x and y components of the object's velocity and acceleration.
Okay, the first two-dimensional kinematic equations we're going to look at are used for projectile motion problems. But before we can get down and dirty with these equations, though, we've got to know how to find the magnitude of a projected object, so we can use it in our equations.
Now that we're going to get into some heavy equations, we'll represent vectors in heavy, bold type. Let's say a cannonball is shot out of a cannon. The initial velocity of the cannonball makes an angle theta with the ground. Remember that velocity is a vector, so it has x and y components. And remember how we found the magnitudes of the components? Well, the magnitude of the x component of a projected object is found using the formula v sub ix equals v initial times the cosine of theta. And the magnitude of the y component is found using the formula v sub iy equals the initial velocity times the sine of theta. So these are the equations for finding the magnitudes of the x and y components of a projected object's velocity.
But before we can get gritty and grimy with the projectile motion equations, we also have to learn a special number. Just learn it, love it, and keep it in your back pocket for later. It's the acceleration due to gravity. You know, when the apple fell on Isaac Newton's head, he figured out that there must be a force that makes the apple fall down. But since this is a dramatization of actual events, we have used our artistic license to embellish a little.
The acceleration of any object due to gravity at the surface of the Earth is 9.8 meters per second squared.
Since gravity creates a force pulling an object down towards the Earth, then it is the y component of acceleration, because we've drawn the y-axis up and down. And on the y-axis, assuming up is positive and down is negative, a sub y equals negative 9.8 meters per second squared. But since we use it so much, we'll just use a little g to represent the acceleration due to gravity.
Now that we're a little more knowledgeable about gravity, it's time to get our hands dirty with the projectile motion equations.
The first projectile motion equation is easily derived from the first one-dimensional kinematic equation we learned, our old friend VVAT.
That equation is final velocity equals the initial velocity plus acceleration times time. V sub f equals v sub I plus at. For projectile motion purposes, we modify this equation to find the y component of the object's velocity. Why the y component? Well, that's the up and down component that corresponds to the acceleration due to gravity. The y component of velocity starts out positive as the object moves away from the Earth, gradually drops to 0 when it stops getting higher, and is 0 at its highest point. Then the y component of velocity gets negative as the object falls back towards the Earth. That is, the object finally falls faster and faster. So then the object's y component equals the initial positive velocity plus negative gravity, because the acceleration due to gravity goes downward times time.
So, since we're only dealing with velocity in the y direction, to get our first projectile motion equation from our VVAT equation, substitute v sub y for v sub f, v sub iy for v sub I, and negative g for a. Then we get our first projectile motion equation. V sub y equals v sub iy minus gt. Got it?
Now, the horizontal velocity stays the same during the flight because there's no acceleration in the x direction, only in the y direction. That's why in the first equation, we don't worry about the x component of velocity, because v sub x equals the initial velocity in the x direction, v sub ix, all the time. And that's our second projectile motion equation. V sub x equals v sub ix. The x component of acceleration is 0 for any object undergoing constant velocity, because the object does not speed up or slow down in the x direction. Remember, we're in the ideal world here. But in the y direction, the object goes up, slows down, stops, and then falls faster and faster. So remember, our second projectile motion equation is v sub x equals v sub ix. Got it?
The third projectile motion equation helps us find the distance that an object has traveled in the x direction. This equation deals with the position of the projected object, and it looks like this.
X final equals x initial plus the x component of the initial velocity times time. Or x sub f equals x sub I plus v sub ix times t.
The fourth projectile motion equation tells us the displacement of an object in the y direction.
Y final equals y initial plus the y component of the initial velocity multiplied by time minus 1/2 gravity times time squared. Or y sub f equals y sub I plus v sub iy times t minus 1/2 gt squared.
If you're having trouble remembering where the minus signs are in these equations, they're only in front of little g, the acceleration due to gravity.
Now that we've learned the equations for projectile motion, v sub y equals v sub iy minus gt, v sub x equals v sub ix, x sub f equals x sub I plus v sub ix times t, and y sub f equals y sub I plus v sub iy times t minus 1/2 gt squared, we can do some problems.
Let's say bright as light, the two-dimensional Supergirl shoots a soccer ball when the ball is 1/10 of a meter above the ground. The ball is kicked at 30 meters per second at an angle of 30 degrees. The net is 20 meters away. How high will the ball be when it gets there?
The problem gives us the initial vertical position of the soccer ball, y initial, of 0.1 meters. That's how high the ball is off the ground when she kicks it. The initial velocity, v sub I, is 30 meters per second. Theta is 30 degrees. The final position of the soccer ball, x sub f, equals 20 meters, and because the goal is 20 meters away from bright as light's current position, x initial equals 0. With these numbers in place, we can find the height of the ball when it reaches the goal, which in our problem is the displacement of the y direction.
So out of the four equations we've got for projectile motion, only one has y in it. That's y sub f equals y sub I plus v sub iy times t minus 1/2 gt squared. I know we don't have the time of the ball's flight, t, but we can figure that out.
Here's how we do that. We need to find time, right? So we look for an equation that we can satisfy using the information we already got, and which also has the variable time in it. The third equation, x sub f equals x sub I plus v sub ix times t, looks like our best choice. We know x final and x initial already, and we can use those to find v initial in the x direction. Once we've done that, we can solve for time. So the first thing we need to do is find the x component of the initial velocity, v sub ix.
Remember from our discussion of the components of a projected object that the x component of the initial velocity equals the initial velocity times the cosine of theta. So for our soccer problem, the initial velocity of the ball is 30 meters per second times the cosine of 30 degrees, which is the angle the ball was kicked. So the initial velocity of the ball in the x direction equals 26 meters per second.
Using our third equation, x sub f equals x sub I plus v sub ix times t, we can find time. Plug and chug, and we get that x final, 20 meters, equals x initial, 0, plus v initial, in the x direction, 26 meters per second, times time. So, 26 meters per second times t equals 20 meters. T equals 20 meters over 26 meters per second, and after we crank that out, we find out that t equals 0.77 seconds.
So we know how long the time of the ball's flight is, 0.77 seconds. It takes the ball that long to go the 20 meters to the net. But we still haven't answered our most pressing question. How high is the ball when it reaches the net? Remember, we're going to use the equation y sub f equals y sub I plus v sub iy times t minus 1/2 gt squared to figure out that answer. So far, we've gotten y sub I, which we were given. The ball is 1/10 of a meter above the ground when it's hit. And we've got time, 0.77 seconds, which we've just figured out. Now, we need v sub iy, the vertical component of the initial velocity.
The initial velocity in the y direction, v sub iy, equals the initial velocity times the sine of theta.
The initial velocity is 30 meters per second times the sine of 30 degrees, which is 15 meters per second. So, v sub iy, the ball's initial velocity in the y direction, is 15 meters per second.
Now we have all the numbers we need to figure out the displacement of the ball as it reaches the net. All we have to do is plug and chug.
Our equation is y sub f equals y sub I plus v sub iy times t minus 1/2 gt squared. Or in English, y final, the displacement of the ball as it reaches the net, equals y initial, which is the initial height where the ball was struck, plus the initial velocity in the y direction, 15 meters per second, times time, 0.77 seconds minus 1/2 times the acceleration of gravity, 9.8 meters per second squared, times time squared, 0.77 seconds squared. Whew! Crank that out and you get the y final. The displacement of the ball when it reaches the net is 8.7 meters. We've been saying displacement because we're talking about the change in vertical position from when the ball was kicked to when it reached the net. So basically, the ball was 8.7 meters off the ground when it made it to the net.
That's great, except that our regulation soccer goal is about 2.5 meters high, and Bright as Light just kicked the ball about 3 times that height. Field goal!
Okay, let's try another problem. Suppose Bright as Light wants to shoot an arrow just for fun at a target. She shoots the arrow at an elevation of 20 degrees. After 2 seconds, the arrow hits the target. How far from Bright as Light will the arrow be when it lands?
Remember, in the soccer ball problem, we wanted to know how high off the ground the soccer ball was. We wanted the vertical height. So that's distance in the y direction. In this example, we want to know the distance the arrow has traveled horizontally, or in the x direction.
The question is asking for the distance the arrows traveled in the x direction. So of our 4 equations, use x final equals x initial plus the initial velocity in the x direction times time.
All I know is the angle and time. You haven't told me how fast the arrow is going. How can I do this?
Calm down. We can find the velocity with a little clever figuring. Here's what we're going to do. First, we're going to figure out the initial velocity of the arrow. And then we're going to use that to help us find the initial velocity in the x direction, v sub ix. Once we have that, we'll be able to solve our problem. Okay? So here goes.
We can find the arrow's initial velocity by using our first projectile motion equation, v sub y equals v sub iy minus g times time. To get the initial velocity in the y direction, v sub iy, we have to use one of our component equations for an object in projectile motion. Remember, the initial velocity in the x direction, v sub ix, equals the initial velocity, v sub I, times the cosine of theta. And the initial velocity in the y direction, v sub iy, equals the initial velocity, v sub I, times the sine of theta.
In our equation, we have to find the initial velocity in the y direction, v sub iy, so we use the formula v sub iy equals v sub I times the sine of theta. Substituting v sub I times the sine of theta into our equation, we get that v sub y equals v sub I times the sine of theta minus gt. We were given the angle, theta, at which Bright as Light shoots the arrow as 20 degrees. We were given the total flight time, t, of 2 seconds. But the time in the y direction is 1 second, because in the absence of air resistance, it takes the same length of time for the arrow to rise as to fall.
All we have to do is plug in our numbers to solve for v sub I. Remember, v sub y is 0, because when the arrow is at its highest point, its velocity is 0. So, v sub y equals v sub I times the sine of 20 degrees minus g, 9.8 meters per second squared, times t, 1 second. The initial velocity equals 9.8 meters per second over the sine of 20 degrees, which is 28.7 meters per second. So we see that Bright as Light shot the arrow with an initial velocity of 28.7 meters per second. See? No sweat. Now we have the initial velocity of the arrow, 28.7 meters per second.
But in order to use our equation, x sub f equals x sub I plus v sub ix times t, to find x final, the distance to the target, we need to find the initial velocity of the arrow in the x direction. Let's look at all the information we've got and figure out how we can find the initial velocity in the x direction, v sub ix. We just found out the initial velocity of the arrow, 28.7 meters per second. So, we can find out the initial velocity in the x direction by using the formula for the initial x component for velocity, v sub ix equals v sub I times the cosine of theta. So, v sub ix equals 28.7 meters per second times the cosine of 20 degrees. And you get that the initial velocity in the x direction is 27.0 meters per second. So, we've got everything that we need.
Plug, chug, and crank it. X sub f equals x sub I, which is 0 when bright as light first shoots the arrow, plus v sub ix, 27.0 meters per second, times the total time of 2 seconds. So, bright as light ends up shooting the arrow 54.0 meters before it hits the target. Wow, they don't call her the two-dimensional Supergirl for nothing.
Projectile motion is when an object is thrown into the air and its path is a curve. If faced with a projectile motion problem, first, break up the object's initial velocity into components, where v sub ix equals v sub I times the cosine of theta, and v sub iy equals v sub I times the sine of theta. Second, set up those kinematic equations. Gravity is the force pulling down on an object in the y direction. The acceleration due to gravity equals negative 9.8 meters per second squared when up is considered to be the positive y direction. The y component of a projected object's velocity, v sub y, equals v sub iy minus gt. The x component of a projected object's velocity is constant, so v sub x equals v sub ix all the time.
For the distance that a projected object has gone in the x direction, x sub f equals x sub I plus v sub ix times t. We find the displacement of a projected object in the y direction by using y sub f equals y sub I plus v sub iy times t minus 1/2 gt squared. Finally, after we set up the equations, remember to keep your positive and negative axes the same from beginning to end. Then plug and chug and crank. And that's it.
Section B, Uniform Circular Motion.
We've learned about projectile motion. Now let's learn about uniform circular motion. That's when an object moves around a circle with a radius r at a constant velocity v, like when I swing this whistle in a circle.
The force that makes the object follow the curved path is called centripetal force, which we label F for force sub c. Centripetal means center seeking. So, the centripetal force is directed towards the center of the circle. The velocity is always perpendicular to the centripetal force. For an object in uniform circular motion, the vector of centripetal force, F sub c, is always perpendicular to the vector of velocity, v.
Because it's changing direction at a constant rate, an object moving in uniform circular motion experiences an acceleration which is constant in magnitude, and which is also directed toward the center of the circle. This type of acceleration is called the centripetal acceleration, a sub c. You can find the centripetal acceleration by dividing the velocity squared by the radius. A sub c equals v squared over r. And since v squared equals v times v, we can remember it by saying a vv over r, or ever, or aver, or aver.
Let's say Bright as Light is driving an uber mean machine around a circular track with the help of her friend, and the car's centripetal acceleration is 242 meters per second squared, and the car's velocity is 220 meters per second. What is the radius of the car's path?
Technically, at that acceleration, her guts would fall out. But this is an uber mean machine, so pretend that this acceleration won't physically affect Bright as Light. Let's see if our equation is of any help here.
You have the equation that the centripetal acceleration equals velocity squared over the radius. Solve for r and you have that r equals v squared over a sub c. Plugging in the numbers for Bright as Light, r equals 220 meters per second quantity squared over 242 meters per second squared. Squaring 220 meters per second, we get 48,400 meters squared per second squared. Divide that by 242 meters per second squared, we get 200 meters. See how the units cancel out and we're just left with meters? Therefore, the radius of the circular path traveled by Bright as Light and her uber mean machine is 200 meters.
When an object is in uniform circular motion, the time in seconds it takes to complete one orbit is called its period.